All right, here is finally the last example. Feels like these are taking forever. Where we're trying to figure out the volume of a solid of revolution using the washer method or the disk or washer method, although I think all the examples has been the washer method. And what we're going to do, the reason I want to do another example is because we're going to rotate around a vertical line just like we did in the previous example. In the previous example, the vertical line we rotated about was the y-axis. This time we're going to rotate around a different vertical line. I guess the line x equals 6 is what I chose for this example. And what you'll see is it's pretty analogous to the difference between our first and second example where we rotated around horizontal lines. First we rotated around the x-axis and then we rotated around some other horizontal line and you had to be a little bit careful with the radius. It's the same idea here. So we started out kind of the same way we've been starting it out. It's handy to have a little bit of a graph to reference. So I drew you the picture over here. We have this straight line y equals 2x and this parabola y equals 1 half x squared. And those bound this region. And just by looking at the graph, it appears that the 2 points of intersection are 0, 0. And then up here at 4, 8. Rather than just confirm these like I did in the previous example, I'm going to show how if you didn't have the picture at all, you could come up with those two values on your own. So what you'd want to do is first take these two equations and solve them for x. So if I multiply both sides of the equation by 2, I get 2y equals x squared over here. And then if I take the square root of both sides of the equation, I get that the square root of 2y is equal to x. And then over here to solve for x is a little bit easier. I just multiply both sides by a half, and I get that x is equal to half of y, or y over 2 if you prefer. And if x equals this and x equals this, well then this equals this. So the square root of 2y must be the same as 1 half y. And this is an equation I can solve. Sure would be nice if this didn't have a square root here. Well, I can get rid of the square root if I square both sides of the equation. So I got 2y equals 1/4 of y squared. And now to solve this, all I got to do is set it equal to 0 and factor. So maybe I'll subtract 2y from both sides of the equation to get 1/4 of y squared minus 2y equals 0. And then if I factor a y out from both sides of the equation, I'm left with 1/4 of y minus 2 in the parentheses. So I got sometimes something equals 0. That happens if either y equals 0 or 1/4 of y minus 2 equals 0. So this solution's already done. And for this one, I'll add 2 to both sides of the equation and then multiply both sides, and I get 8. So what this appears to be telling me is exactly what I thought I saw from the graph, that y equals 0 and y equals 8 are the y coordinates of my points of intersection. And note that I'm concerned with my y coordinates of my points of intersection, not my x coordinates of my points of intersection, because I'm going to end up integrating with respect to y. And how do you know you're integrating with respect to y? Well, anytime you're using the disk in the washer method and you rotate around a vertical line, you'll always be integrating with respect to y. And the reason why you're doing that is because they'll end up being horizontal slices that look like washers, that have the volume of a washer. So y will be the thing that's changing. If you can look at this and kind of see what the solid that you'd end up with if you rotated around this line, it's great. If we rotated around the y-axis, which we're not doing, this region right here, we'd kind of get this cup with a V-shaped interior, I guess. But that's not what we're doing. We're rotating around this line. So what it'll kind of look like, best I can draw anyways, would be this. So instead of having a cup with a V-shaped interior, which is what you'd get if you rotated around the y-axis, we have kind of this tunnel, I guess. I don't even know how to describe this. It's hollow all the way through, so you could walk from the top all the way down. I don't know if you were coming up, you'd notice that it's getting narrower and narrower as you get higher and higher, but it never closes in. It's kind of a tunnel, for lack of a better word. But you don't need to see all that. All you need to see is that a horizontal cross section of this tunnel would make a washer. And that washer would have an inner radius and an outer radius. And the inner radius I would think of as the distance from my axis of rotation to this curve. And my outer radius I would think of as the distance from my axis of rotation to this curve. So if I let this represent my outer radius and I let this represent my inner radius, then I can take the formula that I have to figure out the volume of this solid, which is really just exploiting the fact that we know the area of a circle, and the area of a washer is just the area of the outer circle minus the area of the inner circle. So I get this pi r squared minus pi r squared. Well, capital R represents this length, whatever that ends up being, and little r represents this length. I'm like, all right, this all seems easy enough. Well, this is where it gets a little bit challenging. Figuring out capital R and little r isn't quite as obvious as you'd think. Yeah, capital R comes from this line, not from the parabola, but from the line. So I'm going to have to reference this equation, y equals 2x. But it's not the y coordinate that I'm interested in, it's the x coordinate of this line that I'm interested in, because what I'm interested in figuring out is the horizontal distance. So I need to know what the x-coordinate is. And you're like, oh, the x-coordinate is just 1/2 y. Right, but capital R is not 1/2 y. This 1/2 y represents the distance from the y-axis to this curve, which again is not what I want. I want the distance from this axis of rotation to this curve. However, since I know the distance from the y-axis to the curve, and I know how far the axis of rotation is from the y-axis, it's easy enough to just subtract those two to figure out capital R. What I'm saying is because this is 6 away from this, if I take this entire distance to be equal to 6 and subtract off this 1/2 y part that I don't want, it'll leave me with capital R, the radius. Capital R is just 6 minus 1/2 y. Similarly, to figure out the length of the inner radius, I'll take advantage of the fact that I know how far it is from the y-axis to this curve. And you're like, oh, this curve right here, right? 1/2 x squared. Yes, but 1/2 x squared represents the vertical distance, the height of this curve. I don't want to talk about the height of this curve. I want to talk about the x value of this curve, which is this equation. The x coordinate on this curve is always the square root of 2 times whatever the y coordinate is. So for a given y coordinate here, the distance from the y-axis all the way to this curve is just the square root of 2 times y. But that's not what I want. I want to know the distance from this curve to my axis of rotation. But all I got to do is the same thing where I exploit the fact that the distance from the axis of rotation to the y-axis is just 6. So therefore, little r would be the whole 6 minus this square root of 2y part. If you can see that capital R and little r are represented by these two equations, you got all the stuff that's new for this section, and now it'll just be repeating stuff we've done in the past. What I was trying to do is write something here that was equivalent to what I have above. My bounds of integration are 0 and 8, as I figured out earlier on in this process. And what I really want is pi times capital R, which is what's written in blue here, squared, minus pi times little r, which is written in red, squared dy. And the least interesting part of this problem is where we actually do some calculus and we evaluate this integral right here. We have constants, so we can pull those out in front. That's the pi. So I have pi times the integral from 0 to 8 of, I got these parentheses. I bet those will be a pain. Maybe I should expand things out and call the first parentheses 36 minus 6y plus 1/4 y squared. And then I can call the second parentheses 36 minus 12 square root of 2y plus 2y. Both of those just coming from foiling out from expanding these two binomials. Notice that the second one I had to leave it in parentheses because I want to subtract this entire thing. Now I can combine some like terms, clean some stuff up, and then figure out an antiderivative. 36 minus 36, how convenient, those go away. Negative 6y minus 2y sounds like negative 8y. There's nothing I can do with this 1/4 y squared, so I'll just leave that alone for now. And then I need to subtract negative 12 times the square root of 2y. So that sounds like plus 12 times the square root of 2y. And before I do antiderivatives, I know I said I'd do antiderivatives in this step. I want to clean this thing up a little bit, because if you leave it in this form, it's going to make your work a little bit harder when you do the calculus. So as much algebra as you can do ahead of time will be that much less calculus you have to do later. The way to think about this is the square root of 2 times y is the same as the square root of 2 times the square root of y. So if I wanted to write this as a coefficient times y raised up to some power, because that'll be conducive for figuring out antiderivatives, my coefficient would be 12 root 2, and then I would have times the square root of y. And I'm not going to leave it as the square root of y. I'm going to write it as y to the 1/2 power, because writing my variables in exponent notation instead of radical notation makes the calculus a little bit easier. Finally, I get to take some antiderivatives. The antiderivative of negative 8y is negative 4y squared. The antiderivative of 1/4 y squared is 1/12 y cubed. In the antiderivative of this last term, let's see, my new exponent on y will be y to the 3/2 power, but then I'll need to have an additional 2/3 out in front, and 2/3 of 12 is equal to 8. So I have 8 times the square root of 2. And then this needs to be evaluated from 0 to 8. All right, I wonder if I can figure out this mess without using my calculator. 8 squared is 64. 64 times negative 4, I think, is negative 256. 8 cubed divided by 12, I don't want to figure that out, but I guess what I could do is I could think about 8 cubed as 8 times 8 times 8. And then 2 of those 8s give me 64. And the last 8 and this 12, I can simplify a little bit. I can take 4 out of both of them. So what I'm saying is in the denominator, I'll be left with just a 3. And in the numerator, I'll have 8 times 8 times 2, which is 64 times 2, which I think is 128. And for this last term, it's going to be an absolute disaster, but I guess I'll fight through it. I got 8 times the square root of 2, and then 8 to the 3/2 power. I can think about that as 8 to the first power times 8 to the 1/2 power, which is 8 times the square root of 8. And I think that form will simplify pretty nicely in my next step. The good thing, the very nice, the merciful thing, is that when you plug in zeros, you're just going to get zeros, so I don't even have to worry about that. And so if I could just simplify this a little bit, I'd essentially be done. I'm going to wait to put these two together because I'm going to hope that this term will cancel out with some of this. 8 root 2 times 8 times the square root of 8. Well, the square root of 2 times the square root of 8 is the square root of 16, which is just 4. And 8 times 8 is 64. And 64 times 4, oh, that is fantastic. 64 times 4 is 256. So what I get for my final answer after this 256 and this negative 256 cancel out is just 128 over 3 pi. As always, much less important if you can plug numbers in. Most of you will probably just do that on a calculator. What's more important is that you can set this up. I think the big checkpoint is, can you get to this line right here? This is the really important line. And to get this equation, it's tempting to kind of try to find some shortcuts to be like, oh, 6 minus 1/2 y, here's the 1/2 y and here's the 6. It's always just this minus this. And for red, it's always just this same 6 minus this square root of 2y. And you got to be a little bit careful. You can do stuff like that, and your book even, I think, gives you advice on doing that. But I don't think it's a good idea to do that, because if this axis of rotation is on the other side of your bounded region, well, then you're going to be off by a negative when you calculate the radius. And while it won't kill you in this section because our radius gets squared and the negatives will go away, it will come back to haunt you in the next section. So my advice for you, and you can take it or you can completely ignore it, is to focus on getting this line right here and make sure you understand why the capital R is represented by this expression and little r is represented by this expression. I would argue that that is the crux of this entire section. So spend the time there and not so much on antiderivatives and plugging it in numbers. I think that's all stuff you figured out in previous sections.